Hello everyone, welcome back. So in the last video we got introduced to the tangent line problem. We were trying to find the velocity of the ball whose position is defined by this function f of x, and we saw that the average velocity was this quotient here, f of b minus f of a divided by b minus a. And that was the slope of the secant line between these 2 points a and b. But what we really wanted was not the average velocity, but the instantaneous velocity. The average velocity was over 2 points. We wanted the instantaneous velocity at 1 point as this second point B approached A, and we got this tangent line. But we saw when we evaluated that slope when B equals A, as B approaches A, or as B equals A, we got 0 over 0. So what are we going to do with that? We're going to invent calculus. So let's get going. To overcome this problem, we are going to reframe this scenario just a little bit. So we have this same graph, this same concave down parabola, but we're going to call our first point in this case x. And we're going to call our second point x plus h. So we're going to have a first point x, and we're going to separate it by a distance h. That's what this dashed line represents, the distance h between the first and second points. So now instead of having a and b, we have 2 points x and x plus h, because really all we care about is x. We want the velocity at 1 second at x, and our second point is just we need some distance between the first and the second point so that we have 2 points over which to average. So if we let the point a equal x and the point b equal x plus h, now our difference quotient, just plugging in our values, is f of x plus h, because instead of f of b we have x plus h, minus f of x instead of a, all over x plus h for b minus x for a, which simplifies to f of x plus h minus f of x all over h, because positive x and negative x cancel out. So we want the value of this function as h approaches 0, as the separation between these 2 points approaches 0. We again have our tangent line problem. So with this function here, which is called the difference quotient, because there's a difference in the numerator of the fraction, and it's a quotient, it is a fraction. This is the difference quotient that you've seen in calculus. This difference quotient, what it gives us is the slope of the line at any point x, the instantaneous slope of the line at any point x, with a separation h from the second point. And so our problem that we had before is, how do we solve this as h approaches 0? Because when h is 0, we get the same problem as before, right? So when h equals 0, we again get 0 divided by 0, because when h is 0, the top simplifies to f of x minus f of x, which is 0, and the bottom is 0. So now, this problem of finding the value when b approaches a at the 2 points is the same thing as when h approaches 0 of the difference quotient. So this is where calculus comes in, and how we're gonna begin to work on this problem is we're just gonna analyze the behavior of this difference quotient. The behavior of the difference quotient, like what's going on with this difference quotient, because we're trying to solve it as h gets closer and closer to 0. So we're gonna look at how the function behaves. So what that difference quotient really gave us, it was the slope for a given h. The slope for the given h was given by this difference quotient, which I'm writing out again, f of x plus h minus f of x all over h. For a given h, we can evaluate the slope of that line. And we also need an x. So when x equals 1, we can evaluate this difference quotient for x equals 1. And we'd really like it as h approaches 0. So what this statement right here is it's mathematically the statement of what is the velocity of the ball at 1 second. Right? So in physical terms, the velocity of the ball at 1 second was just what the speedometer read on the ball at 1 second. And now we translated that mathematically as the slope of the secant line when x equals 1, which is saying at 1 second, as h approaches 0, which is saying I want the instantaneous velocity, not just the average. And so we can write out this slope function mathematically by plugging in these values for x equals 1, and we're going to leave h as a variable because we want to see how the function changes with h. When we change the separation between the 2 points, how does the value of the slope change? Right? So in this picture, we have this value h. As it approaches 0, how does the slope change? So mathematically, when we just expand this function by plugging in, we see the top becomes -5. We're just going back to our definition of f of x. And our input is x plus h, which is 1 plus h squared plus 25 times our input again is 1 plus h. So this is f of x plus h, where x equals 1, and we're leaving h as a variable, minus the function value at 1, which is -5 times 1 squared plus 25 times 1, all divided by h. So what this quotient right here gives us is the function value, what this quotient gives is the slope for any given separation between the 2 points. So we can start seeing how this behaves. We look at a given value of h, and we look at what the resulting slope is. So when h equals 2, if you evaluate this function at 2, what do you think the slope's going to be? Well, if we look back to our original scenario, right? We found the slope when a equaled 1 to 3. When the first point was 1 and the second point was 3, right? The first point is 1, the second point is 3. We found that the answer was 5 meters per second. And indeed, that's the same thing that's going on here. When h equals 2, our first point x is 1, and because the separation between the first and second point is 2, that means our second point is 3. Because the first point is 1, 1 plus 2 is 3. And the slope is indeed 5 meters per second. If you evaluate this function for h equals 2, you will get 5 meters per second. Similarly, when h is 1, we get that our slope is 10. So that's what we did when we had the 2 points 1 and 2, right? Our h is the separation 1 between our first point 1 and our second point 2. When h is 0, so this is the case we don't know what to do. It's undefined. But if you evaluate this quotient at -1, you'll get 20. If you evaluate it at 2, you'll get 25. So what we're going to do is we know we want the point as h gets closer and closer to 0. We want the value of the function as h approaches 0. So we're just going to graph the function to see what's going on, because we know what the function is doing at every point besides h being 0. So this here's our h-axis. It's saying how does the slope change as we vary h. And on the y-axis here, on the vertical axis, that's the slope of that tangent line for a given value of h. So we can plot our points. If we define this to be 5, 10, to be 15, and to be 20, to be 25. We know that the point -1, 20 exists on the graph. We know the point -2, 25 exists on the graph. We know the points 1 and 10 exist on the graph. We know the point 2 and 5 exists on the graph from just evaluating this difference quotient. But we don't know what happens at 0. There's a hole in our graph at 0. We notice here's the graph. Here's what the graph is doing. For h, if we change h, we can evaluate the value of this function all around 0, but not at 0. But we notice an interesting trend. As we get closer to h on the left side, we're getting right around the value of 15. And as we get closer to h being 0 from the right side, we again see that the value is 15. So we might suspect, hey, I bet if we could evaluate h at 0, you know what it would be? It would probably be 15. So we can make our educated guess that the speed of the ball is 15 meters per second. And what that's called is the limit. This is the limit in calculus. We say what's going on around the function. We don't know what's actually happening at the function, but the limit says, hey, what's going on around it? 15 meters per second. So when we're analyzing this difference quotient for h to find the velocity of the ball, and we see, hey, the answer should obviously be 15, that's the limit, and that's calculus.